Alright, so today I'm going to be talking about something called the Riemann sums. And then I'm going to be using the Riemann sums to finally formally define what an integral is. So if you remember the video I did on approximating integrals through like LRAM, RM, those were a type of Riemann sums. And then now we're finally going to be ready to formally define what a Riemann sum is and use that definition to define what the integral operation is. So remember, our overall arching goal is to find like a way to find the area of an arbitrary curve between some interval. So here we have an interval from a to b, and we want to find the area of the curve from a to b. And this area below the axis, that'll just be negative area, and it'll be positive. And this area above the axis will just be positive. So as you go below the curve, you just you just treat it as negative. So that's the idea or notion of a negative area. But that's just an aside, right? And we called that I kind of told you guys that this operation of finding the area under a curve is known as the integral operation. That's why we're spending a lot of time to formally define what this integral is. So what a Riemann sum basically is saying that on some interval, and in this case between a and b, we split the interval into some arbitrary n subintervals. So we have this overall area between a and b, and we're just going to split it into n subintervals, right? Such that like all the points that we chose between our subintervals, so we have a less than x1 dot 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 all the way less than xn minus 1 is less than b. So this is just saying that the anchor points, or like the points that we choose that define the boundaries of the subintervals, are just between a and b, right? It's kind of obvious, right? And so these points then just find out different partitions. So let's just split it into like a few subintervals. We'll call this x1. We'll call this x2. Notice how I'm like purposely like shifting up the size. So the sizes of the intervals are not constant, and that's by design. And then, similar to what I did in the approximating intervals video, I'm just going to make these like rectangular boxes that sort of try to approximate the area of the curve, that try to act like what the curve looks like. And since I'm like kind of anchoring at the left, you'll see this like big negative that represents the whole curve over here. All right. And so I have these subintervals, right? So specifically, I've divided the interval between a and b into 1, 2, 3, 4, 5, 6 subintervals, right? And I'm gonna call the distances between like each of these, so these widths, I'm gonna call them delta x sub I, right? Where I is just the anchor point. So this distance over here is going to be delta x sub 1, and then this is delta x sub 2, delta x sub 3, delta x sub 4, x sub 5, and then delta x sub 6. All right, so those are my widths of the intervals. And we know that if we were to choose like a point that determined the height of the curve, so if I said, like in this case, I already told you that like the way I'm determining the height of the curve is through choosing this like left point as the height of the curve, and so that serves as my like f of ck, where ck is just the notation that I'm going to be using to determine the, or like anchor height of the kth subinterval. So in all the approximation methods that we had to split the overall interval into smaller subintervals, and then we had to create an approximation of what that subinterval looks like by creating like a rectangle, right? And we needed the height, and the height had to be anchored at some point on the actual curve. And here we're just going to call that arbitrary point f of ck, where ck just serves as some point in our subinterval that's going to act as our anchor height to help us approximate the area of the curve. So in just for the sake of my example here, I've just used all the f of ck's just to be the leftmost point on each subinterval. So this is f of c3 right here, this value, and then this is or sorry, f of c4 because this is the fourth interval. This is f of c5, and then final, like just for clarity, that is f of c6. But the Riemann sum is very general, right? So you could have chosen any point in this interval or for f. So like if I wanted some point on the fourth subinterval, I could have chosen any point on this curve right here to be my f of ck. Similarly, for my third interval, I could have chosen any point over here, right, in this curve to serve as my anchor. And essentially, what the Riemann sums are just taking the sums of all of these like approximate boxes that we created, and that is what the definition of a Riemann sum is. So S of n is the Riemann sum of n subintervals on some overall large interval. Here we're taking it from a to b, and that is simply equal to, and then here again I'm using the sigma notation, which just means sum, k equals 1 to n f of ck times delta xk. So notice how this formula over here is doing nothing but summarizing all of this like mechanics of like creating boxes and summing up the various approximate boxes that I created, right? Because there's n boxes, right? Because there's n subintervals, so that's why I'm doing a sum over n things, and for each of those sub boxes. So yeah, let me actually change the color. Should probably do this more often for the color change. Right. So for each of these n boxes, let me just focus on this box over here that I created. So this on this sub interval between x of 2 all the way to like x of 3, this is the curve, right? I could have chosen a particular point on this curve to be my height point. So f of ck is just my height point. So I could have chosen this point over here, or I could have chosen something over here, and that's fine as well. And so that serves as our height point, and delta xk, so over here, delta x3 is our width point, right? So all this is doing is for each subinterval, right? So we have n different subintervals. For each subinterval, it is creating a rectangle. The rectangle's height is determined by some value on the curve in that interval, and that's up to you. And then it's multiplying it by the height of the, or by the width of the curve. Width of the interval, sorry. Right? So the width of this interval is determined by delta x3, and the height is determined by choosing some point as the anchor point on that interval. So this is how x3 looks on this interval, and we just choose some point on it to act as our anchor point. And that creates a rectangle, and when we multiply the base times the height, we get the area. And since we have n subintervals and we're summing up n areas, that gives us our total area approximate over the entire interval of a to b. And that's what the Riemann sum is trying to define, right? It's trying to get us a formal way to define the area of a curve on some interval between a and b. So we have this Riemann sum definition, right? And the idea is, and I motivated this in the video where I was talking about approximations, is as we increase the number of intervals, so I'm going to start, so as we increase number intervals, right? So there's a plus sign just for me saying increase the number of intervals, we're going to get a better and better approximate of the curve, right? Curve approximate is better, right? And because we get a better approximate of the curve, we get a better approximate of the area. Better area approximate. Right? And when do we get the best approximate? When do we get the perfect approximate of the area under the curve? And that's where perfect approximate, the perfect approximate is when our interval sizes go to 0, right? Because I said that the curve approximate is better as we increase the number of intervals. And when we increase the number of intervals, or this should actually, like, to be more specific, increase the number of sub-intervals, right? Because the interval that we're trying to find the area over, a comma b, is always the same. So as we increase the number of sub-intervals, what we're doing is each of the sub-interval sizes goes to 0, right? Or gets smaller and smaller. If I were to, so here we have, in this example right now, we have 6 sub-intervals. If I were to double it, I have 12 sub-intervals. It must be that some of those 6 sub-intervals right here will get smaller, right? If I were to draw out, like, try to create space for another 6 sub-intervals, right? It makes some of my intervals smaller. So when all our sub-interval sizes go towards 0, we get a perfect approximate of the curve. Because at that point, what we're doing is we're just saying, oh, our sub-interval size is just 0, right? So at that point, it just must be whatever the value of the curve is, right? So that is the main, that's the main motivation. That's the main, concept that you guys must understand to kind of understand the idea of the integral. Is that if we're trying to approximate the area of the curve on some, big interval a to b, if we increase the number of subintervals over which we calculate this Riemann sum over, right, then we're getting a finer and finer approximate of the actual area. And since we're getting a finer and finer approximate of the actual area, we're getting closer to what the perfect approximate is. And when do we get the perfect approximate? It's only when our sub-interval sizes go perfectly to 0, because at that point, we're just finding the area of the curve itself. We're not finding the area of an approximate of the curve. And that's the main, thing behind an integral. So now that I've kind of motivated why sub-interval sizes to 0 lead to the actual area of the curve, and I said the integral was basically an operation to find the area under a curve, let me define the integral. So the definite integral. So now I'm going to define what the definite integral is. So if f is a function on interval a to b, and it's a closed interval, for any partition P of AB, and this just means, by partition P, it's just how you divide the original interval into the subintervals. Let CK be arbitrarily chosen. Arbitrarily chosen on each subinterval. Then then if there exists I such that limit as, and so this is saying this notation over here means the norm of p. That just means the size of the subinterval of p. So that means each of the subintervals as their size tends to 0. And then over here I'm just defining the Riemann sum that we defined earlier. K is equal to 1, f of k with ck times delta x of k is equal to I. So this is just the same Riemann sum we saw earlier. We're only saying what I verbally said before, that we're going to make each of those subinterval sizes go towards 0. And that means that if there exists some number I such that this number is equal to I, then no matter how P is chosen and CK is, or CK are chosen, since there are multiple CKs, then F is integrable on A to B, and I is the definite integral of F over A to B. And so now we've formally defined what an integral is. And I'll explain what this last two sentences mean, or last two lines mean. But we've formally defined what what an integral is. We defined that the Riemann sum is just us making those rectangular approximations over each subinterval for the curve. And when we take the length in the limit as the length of the sizes of the subintervals go to 0, the value of the sum, we're assigning that value of the sum that we get when we take the limit to some value I. And what we're saying with these last two sentences is no matter how p is chosen, so remember in the example where I divided that interval from a to b into irregular size partitions, so there's one partition where delta x1 was much bigger than delta x2. So it doesn't matter how you choose these partition sizes, they can be randomly chosen. And the second part saying no matter where you choose the ck, so we can choose ck to be somewhere closer to the edge of the first interval, but we can make it closer to the starting of the second interval for the ck 2 over here, right? So it doesn't matter where you choose ck as well in each of these subintervals. Those you can do it however you like. What happens is when you in the limit, as you take the limit, if we get some value I that's a constant, then we're saying that f is integrable. That means you can integrate that function, and the value that it spits out when you do the sum in the limit is known as the definite integral. So we've defined what the definite integral is. We're basically saying, oh, it's the value that you get when you do that operation of approximating the area of the curve, except we're making the interval sizes in our approximate very small. And hence, this value of I that we get when we make the interval sizes to 0, it must be the area under the curve, right? And that's all we're saying. And so from the last part, this part about no matter how p is chosen, it might just be easier for us to reason about integrals if we chose p in a specific way, because the definition over here says oh, we don't really, there's no difference of how we choose p's, and so we are free to choose p's in any way as well, right? So let's just choose a p, the partitions, how we make the partitions in a way that makes our other arguments down the line and our understanding down the line easier. And so let's choose the p in a way that we're just gonna say delta xk, because the partition size, the size of partition is basically delta xk, right? So I claim that I'm going to make all the delta xk simply equal to b minus a over n. So I'm saying that if I have n subintervals that I want to create between b minus a, I'm just making all these subintervals have the same size. Okay? And now I can create a second definition of the integral. And um, this motivates or we get second definition through this. And our second definition is just limit as n tends to infinity, sum of I equals 1 to n of f of ck times delta xk. And so that means that all delta xk are the same size. We're saying that this is the size b minus a over n. And by doing this limit as n tends to infinity, we're saying that we're creating an infinite number of intervals. Infinite number of intervals between a and b, because we're still just the problem remains the same. We're concerned with finding the sum of the areas under the curve on this interval between a and b. And so we have now just defined a special way to create the partitions, because our previous definition said we can do anything we want. We're free to choose how to create the partitions. The correctness doesn't change. So we chose the partitions in a way that makes life easier for us by just splitting the length of the big interval into n equally sized intervals, and then we're just going to take the limit, and we're just going to create an infinite number of subintervals. And so we found a new definition of the integral, and that's just saying the integral is simply the sum of the areas, or the boxes that we make when we take an infinite number of subintervals. And yeah, that is the formal definition of the integral. This was a bit more abstract, but hopefully it gets a better intuition about what the integral actually is and what operation it does and why it finds as the area under the curve. And next time, I'm probably gonna introduce all the fun semantics of the integrals and start doing numerical problems.